Okay. Hello, everyone. I'm Walid Shakir from Wallace University, and I'm going to represent our latest work with Professor Alexander Klemchik from University of Lincoln. And this work is the simulation study for robot-based incremental forming. So basically, what is the incremental sheet forming? It's an innovative process that uses progressive plastic deformation to cause like sheet deformation, as we can see in this demonstration. Can you please? Okay. So as you can see here, the like in the effector hemispherical tip is attached to the tool to cause the plastic deformation in the sheet. And this process has two types. It has the single point incremental forming as the one we can see in the video, and it has the double-sided one. This work is dedicated to the single point incremental forming. And this process has many advantages over the conventional way because it is a flexible process. There is no tool specification required for this process. And there are many advantages over the deep drawing methods that you used previously. Like, for example, here, if you are using the conventional way, you have to design a die for each part, while here you just define the tool path. Although these advantages, it experiences some limitations, most specifically the geometrical errors. And these geometrical errors, it happens because the spring back effect, as we can see here, when you release the loads that you apply to the sheet, due to the material elasticity, the sheet deform back due to the spring back effect, and it caused like undesired shape at the end. So in this work, we're going to investigate the tool path definition because it's greatly influences the accuracy of the process, and we will show the like propose a model to overcome this spring back effect. So as I mentioned, the accuracy of the work is affected by the tool path definition, and in literature there are like the most often ways to define the toolpath is the Z-level toolpath, is the one we see here, and the helical or spiral toolpath. In the Z-level toolpath, the components are produced by cutting the component using equidistant planes, and the spiral toolpath is basically the helical one. So in the toolpath, for the Z-level one, this is the algorithm to create this toolpath. Like you basically define the increment, which is the steps, and you generate the X and Y and Z coordinates using the cosine and sine. This is a straightforward approach. And this is the result of the Z-level toolpath definition. For the spiral one, the spiral one is much better in the single point incremental forming because it, while like moving the tool, it keeps like a gradual helix in the depth direction, and these are the parameters used to define the spiral toolpath. You start with the maximum radius and you define the minimum one. And for this study, we are working on the truncated cone. You also define the step depth and the wall inclination angle, which is theta, and the change in radius that you're gonna use to generate the X and Y Z coordinates. And the result of this code, it will generate the spiral toolpath or the helical one, as you can see here. Okay, after generating the toolpath, it's important to simulate this toolpath before going to the actual operation. And in this simulation, we are using RoboDK, and the importance of simulating the toolpath is to check the singularities, if it will cause singularities or not, and also to check the joint limits, and also to check if it will exceed the limits, for example. And to visualize it, actually. So we have used the FANUC robot, And first, the workpiece has designed using SolidWorks, and it was controlled using the RoboDuCabe offline programming tool for simulating the tool path. And this is the simulation. It's better to. Yes. So as you can see here, the tool path was properly defined because the end effector like coincides with the inner walls of the workpiece. So after making sure that the tool path was generating in a proper way, it is the time to go to the numerical simulation of the single point incremental forming. And to do that, first it was done using Abacus computer-aided manufacturing tool. Should I move on? Okay, and to do that, you have to go through these steps. This is some practical steps to do the simulation. You first start with the geometry for the sheet and tool, and after that you define the material and you go through material calibration, and then you make the assembly in which you define the contact between the aluminum with the following material properties. And as I mentioned, about the assembly and the meshing, it is shown here. So you define the contact between the tool and the sheet, and after that you do the meshing process over the sheet to discretize it into elements and the node. It is worth mentioning that also about the boundary condition. In order to implement that, you should have at least, there should be like 4 boundary conditions here. The first one is to fix the sheet, like not to move, and the other 3 are dedicated to the tool movement in the 3 direction, X and Y and Z. After that, you solve this finite element method problem, and we have selected these 3 standard output identifiers to evaluate our results. So we first use the plastic equivalent strain and the displacement in the Z direction, in negative Z direction, and the von Mises stresses. Like this is a scalar quantity that represents the material in elastic deformation, and the displacement in the Z direction, it's like straightforward identifier, and the von Mises stresses, it's for indicating the yielding of the material. Like for example, if this value is greater than the yield strength of the material, so it indicates that there is a plastic deformation happens here. If you can see, like most of the values of the equivalent plastic strains, like they are almost 0, and this is due to the spring back effect that I mentioned in the earlier in the presentation. So like most of the values like goes to 0. So like this bring back effect makes the sheet deform back, which results in inaccurate shape. So if you can please run the demo, like this one. So as you can see here, this is the numerical simulation of the process in an Abacus software. So it's incrementally deforms the sheet until until it makes the truncated cone, which is our desired shape. So the results was evaluated using the relative error between the desired depth and the simulated one. But here we used the final depth of the simulated shape, and it was found like its relative error is 0.5 like percent. Like since the desired depth was like 40 millimeter and the simulated one was 40.2. However, when we compared like point by point from between the sheet state and the simulated one, we found like a maximum error of 1.44 millimeter. So like as a result, we have proposed an algorithm to overcome these errors. it is worth mentioning that like in this process there is like the material geometrical error and the robot error itself due to the low stiffness of the robot. So the proposed one that we used here, like we will like propose a model for the spring back effect to overcome the material errors, and another one which is a stiffness based error compensation, and this one is used to eliminate the deviations that happen to the end effector due to external forces, because in this process the forces is extremely high, which makes the robot like deviate from the nominal path. And we will combine also the a closed loop feedback, which is like model predictive control. And as a result, we will feed all of these to a toolpath fusion model to like optimize the process and get rid of the errors here. This is a diagram of what I have just explained. The errors is like separated to the spring back, the material, and the tool deviation of the robot. By the time of submitting this paper, like we didn't have these results, but right now, like this one has been submitted to a conference, and this one as well. So this is their toolpath, and after you do the spring back compensation, you get another toolpath, which would be an input for the stiffness-based algorithm to generate the third toolpath, which is the final one. This is the last demo I have here. So as you can see here, when the robot like applies some forces to the sheet, it got the reaction forces. And I'm using like virtual joint modeling method to calculate the deflection. If you can please go to the end of the video. Yeah. I just want to show the final. Yes. So we are using this deflection map to generate the new toolpath that accounts for both errors, the spring back effect error and the toolpath deviation due to the forces error. So to wrap up, in this study, we investigated the toolpath definition for the spring back to the incremental forming process, and we have used like two strategies: the Z level and the spiral toolpath. And the toolpath was simulated using RoboDK. And after that, we showed like some practical tips for implementing the single point incremental forming using Abacus software. The relative error was found to be 0.5, which is quite acceptable, but the maximum error when we compared like point by point between the sheet state and the final one was 1.44. So as a result, we proposed an algorithm to improve the overall accuracy and considering like the material and the robot errors. So that's all. Any questions?
Thank you for the report. Any questions, colleagues? From the distant colleagues, no any question, but I want to ask you about the 0.5 percentage.
Mm-hmm. Yes.
How did you make such currency 0.5?
Okay, so as I mentioned, for this study, we used a truncated cone shape with a desired 40 millimeter, and the simulated depths that we got from Abacus, like yes, this one. Yes, if you have a look at the value here, it is 40.2 millimeter. So if you calculate the relative error, between these two values, you will get like just 0.5. But this is calculated over the final depths that we achieve. But for example, if you like we have here, yes, we have here a desired toolpath, which I would say our ground truth, and here we have a simulated one. If you compare the data we have got from Abacus with the desired ones that I have just shown, like point by point, you will get a maximum error of 1.44.
1.44, it will be more than 8%, maybe, yes?
Yeah, something like this.
0.2, it's 0.5.
Yes, this is like point by point, the difference between each points from the desired one and from the simulated one. There was a maximum of 1.44 millimeter.
And you also told about the practical application of your research in the end. You're like, you can recommend this for some.
This one, I mean.
For them, what? Yes, you. To solve the practical application, you show this form, the plastic form, this, and how we can apply these results in the future. And maybe you have some ideas how to realize this in the practice.
Yes, right now we are working on the setup in our university to implement the. Actually, this is a part of an Indian project. It's an Indian project. It is an industrial one in India right now, and we are working on a partnership between our university and their institute there. So it is actually an industrial project.
You're from Innopolis?
Yeah, I'm from Innopolis. I'm second year master's student.
Communication for me. So, and also no indication. Thank you for the report, for the participation, and we will go to the next our report. The